So good morning everyone. Now we are going to study particle in a box. As you know, we have been analyzing various one-dimensional problems. That is different examples for the one-dimensional solutions of Schrodinger equations. So today our example is particle in a box. We can also say that when a particle is confined in a box, it can also be equivalent to, okay, let me draw a particle in a box. So I'll give the dimension 0 to, that is in the x direction, 0 to small a, right? This is actually equal to the following situation. If we have a potential, a square well potential with infinite, with wall of infinite height, that is also equivalent to this situation. Yeah, I will write it as same dimension as that of a particle in a box. If this wall is of infinite height, these two situations are the same. We can also call this square well potential again, square well potential with infinite walls, again one-dimensional infinitely deep potential well, infinitely deep one-dimensional potential well. If you come across all these three different situations, you should understand that all are the same. Because if the wall is too high, the particle may not be able to come out of the well. That gives the same situation as that of the particle confined in a box. Okay. Now, when we say that the particle is confined in a box, we have to think that when there is we have to define the potential of it. V of x is equal to 0 between 0 less than x less than a. As you can see, the particle experiences no potential. That means it doesn't experience any force acting on the particle. Okay, when it is in the wall, I mean inside the box. So it doesn't experience any force. When potential equal to 0, we have to understand that no force acting on the particle. Okay. Now, what about the remaining cases? So if 0, I mean x less than 0, v of x is equal to infinity for x less than 0 and x greater than a. Okay, so we can say that the particle is not able to come out of this box, this well, unless the potential is 0. So since there are walls or it is confined in a box, we can say that it experiences a force so that it cannot come out of the box. So this is the situation now. So we can say that there is no loss of energy. That means total energy of the particle is a constant. So our conclusion regarding this is total energy is a constant. So these are the introductory ideas regarding the particle in a box condition. Okay. Now let us go for the Schrodinger equation and its analysis. So you have to remember a few things. I'll write it somewhere here so that it will be useful when we derive Schrodinger equation. So first of all, our box 0a, our particle is somewhere here, and v of x is equal to 0 for 0 less than x less than a, and equal to infinity for x less than 0 and x greater than a. Okay, so this is our condition. Now what we have to do is write the Schrodinger equation. So according to our basic time independent Schrodinger equation, in order to find a solution for such a case, we have to avoid our potential, like what we did in the case of a free particle. We have to avoid potential and write Schrodinger equation. So our Schrodinger equation will be minus h cut square by 2m d square psi by dx square plus, yeah, potential part will be 0, so I won't write that, is equal to E psi. So this is our Schrodinger equation. Now what we have to do is we have to calculate a suitable solution for this. For that, we are just going to rearrange it. Let me take this one to the right hand side. So d square psi by dx square is equal to minus 2m goes up and h cut square goes down, 2m e by h cut square into psi, and I'll take this term also to the left hand side. So this one plus this is equal to 0. I'll take this term 2me. Okay, I think I'll write it somewhere here itself. 2me by h cut square is equal to k square. Okay, so I can write it as a k square instead of this one. So d square psi by dx square plus k square psi is equal to 0. So this is our Schrodinger equation of our standard form. Now we are going to assume a general solution. This actually look like if the particle starts moving or starts colliding, it will be colliding here, then here. So that may be equivalent to a standing wave pattern formed in the box. So let us assume the possible solution as psi of x is equal to a sin kx plus b cos kx. Okay. Now we have to apply the boundary conditions. We are already familiar with the boundary conditions. boundary condition says that at x equal to 0 and x equal to a, the wave function reduces to 0. That means we know that particle is inside this box, not at the walls or beyond the walls. So our condition is going to be psi of x is equal to 0 at x equal to 0 and x equal to a. So let me take this first condition and apply it here. So psi should be 0 when x equal to 0. A sine 0 plus b cos 0. As you know, cos 0 is 1. So b, this term will be existing there, b, and sine 0 is 0 itself. So this term vanishes. So this is equal to 0 plus b. This is not a valid case. As you know, the left hand side is 0. So b is equal to 0. The condition you get by applying this part is b is equal to 0. So let me give the value. Let me give the value. So psi of x is equal to, so b should be 0. That means it is a sine kx. Condition we obtained is b is equal to 0. Now apply the second condition. If we apply the second condition, you should have psi of x is equal to 0 when x is equal to a sine ka. So for this case, we have to find a value of ka such that sine is 0, because a cannot be 0, so that it equals 0. So that accordingly, that condition is given like n pi is equal to ka. Okay, so if ka is equal to n pi, you know that sine n pi turns out to be 0. That means 180, 360, all those things. Sine of 180 will be 0. So the multiples of 180 will also be 0. So we can, from this, what we get is ka is equal to n pi. Okay. So if ka is equal to n pi, you can take k is equal to n pi by a. So we already have an equation for k square. In the beginning, we have assumed k square like this. So 2me by h cut square is equal to k square. So you are able to apply this condition now. Okay. Now k square is n square pi square by a square. This is equal to 2me by h cut square. So you have energy E is equal to, E is here, so I'll take all the remaining terms to the right hand side. So E is equal to n square pi square h cut square by 2ma square. So I should write somewhere here. Okay. E square is equal, so E is equal to, this is the condition we get, n square pi square h cut square by 2ma square. Okay, so this is results. This is the initial condition. This is the condition we got from the first modification of Schrodinger equation, and this is another condition we have assumed based on the initial condition, and this is what, yeah, this one is the fourth one we got from the by applying third one, and now we have this one. So there are many important results here. Okay, so now we have the value of E, and the psi of x can be rewritten like, yeah, psi of x is using the value, psi of x is rewritten as by giving the value of k here. So we can write it as n pi by a. This is the general equation. I think I like that also. 6 psi of x is equal to a sine k is n pi by a, n pi by a into x. Okay, now I can rub it. Okay, now let me find out the possible values of energy. So the possible energy values can be determined by giving the values of n. E square is n square pi square h cut square by 2ma square. Give n from 1 to 3. So if n is equal to 1, E1, no, it is not square. E1 is 1 square pi square h cut square by 2ma square. Now when n is equal to 1, n is equal to 2, you have E2 is equal to, you should have 2 square, so 4 pi square h cut square by 2ma square. Now when n is equal to 3, it goes like that. E3 is equal to 3 square 9 pi square h cut square by 2ma square. So you will have values of energy. If you wish, you can also avoid h cut by expanding h cut as h by 2 pi, and you will have energy in terms of h itself. So the pi may get cancelled because h cut is h by 2 pi. Okay, so if you rewrite like that, the equation becomes E is equal to n square pi square h square by 2 pi square 2ma square. So pi square get cancelled from here, and here you have 2 square is 4, so 8ma square. So this is n square, sorry, h square by 8ma square. This is also another way of writing the same thing, the energy value. Okay, you need not bother about that. If you would like to stick on to this one, you need not worry about that. Okay, these are two different ways of expressing it, in one in terms of h and other in terms of h cut. Okay, now let us go for the expression of wave function. We have psi of x is equal to a sine n pi x by a. Okay, I think we can plot this and check how it looks like. So when we plot this one, so this is 0 energy, this is E1, E2, E3, E4. when we find the values and plot it, by applying the constants, suppose we have dimensions, yeah, apply the value of A as well. So what you find is this is the energy level for n is equal to 1, and this for n is equal to 2, this for n is equal to 3. This is a kind of representation, n is equal to 4. So what you observe is the gap between various energy levels increases as n increases. So if you find the difference between E2 and E1, you will get as E2. E2 is this one, E2 minus E1. So I think I will write it somewhere here itself. Okay. E2 minus E1. That is the ideal case of En plus 1 minus En. Okay. Here our N is 1. Okay. So give the values. So what you have is 4 pi square h cut square by 2ma square minus pi square h cut square by 2ma square. So what you have is 3. This is this pi square h cut square by 2ma square is a common thing. So you have 4 minus 1 into pi square h cut square by 2m a square. That means it is 3 times pi square h cut square by 2m a square. This 3 can be generally written as if we give, because n equal to 1, you have if you write 2n plus 1 and give n equal to 1, you will get it as 3. So we can generally write this one is 2n plus 1 into our basic equation, that is E1, because pi square h cut square by 2ma square is E1 itself. So this is the general difference in energy. So as you can see, the difference is getting increased as n increases. So that is the analysis of our energy level, energy spectrum. Okay, now let us go for yeah, this is the energy level diagram. Okay, energy level diagram. Now let us go for the sixth one, that is our wave function. We can write that also. En plus 1 minus En is equal to 2n plus 1 E1. Okay, now let us go for the wave function. Wave function, as we know, psi of x is equal to a sine n pi x by a. Okay, so once we have the wave function, we have to think about the normalization. As you know, the normalization condition says that integral minus infinity to plus infinity psi star psi d tau is equal to 1. Here we are standing in the one dimension, so d tau should be dx, and also our limit is 0 to a. Our particle is confined in a box. So we have to change our integral from 0 to a. Psi star psi dx is equal to 1. So if you normalize it, if you do this procedure, what we are going to get is we can find a constant, so that the inner product of this wave function, or the length of this vector, can be reduced to 1. Okay, So let us apply the condition 0 to a sine n pi x by a, then psi is again a, this is a star, okay, sine n pi x by a dx is equal to 1. So you have a star a that can be taken as a mod a square. Let us take it outside, mod a square, and you have two sine functions, so sine square n pi x by a integral 0 to a dx is equal to 1. Now we can write this as a 1 minus cos x, cos to x. So sine square, the expansion of sine square theta is sine square theta is 1 minus cos 2 theta by 2. Okay, so let us use that identity, mod a square integral 0 to a 1 minus cos 2 theta means 2n pi x by a dx divided by 2. So this 2 can be taken outside because it is a constant, is equal to 1. Okay, now integrate it. First term, integrating the first term, you have mod a square by 2 integral dx. First one is x between 0 and a minus second term. If you integrate it, you will have sine sine 2n pi x by a by constant should come down to n pi by a between the limits 0 and a is equal to 1. But the problem is that if you apply a here, a or 0 here, sign turns out to be 0. So we need not use this one to apply limits and finding the values, because this term will be 0 and either applying 0 or a, irrespective of the limits, it will be 0. So you can just avoid the second term. Okay, avoid the second term. This is equal to 1. So apply upper limit is equal to mod a square by 2. By applying the upper limit, a minus 0 is equal to 1. So you have you have mod a square is equal to, I'll take a and 2 to the right hand side, so 2 comes up and a comes down. So a is square root of 2 by a. So you can apply it here, psi of x is equal to square root of 2 by a into sine n pi x by a. So this is our normalized wave function. If you find the normalization, if you apply this value and find integral 0 to a psi star psi dx, it will definitely be 1. That means the inner product of psi to itself is 1, or the total probability of finding the particle within the box is 1. That is the meaning of it. So that is all about the normalization of wave functions. Now let us also check the orthogonality. We have to check the orthogonality of our wave function. That is also asked as a problem for your examination. So let us analyze that also. Let us check orthogonality of the wave function. Okay, let us, in order to check the orthogonality, we have to use psi, two distinct wave functions, psi n of x and psi m of x. So psi n of x can be written as our constant square root of 2 by a. Yeah, I'll write it as 2 by a. That is our wave function. Okay, so 2 by a sine n pi x by a, and also psi m of x is equal to again 2 by a sine m pi x by a. Now, for these two wave functions, if they are orthogonal, the condition is going to be like this: integral 0 to a psi n of x psi m of x dx should be 0. That is their inner product. And if we use the bracket notation, psi n of x psi m of x is going to be 0. For the normalization condition, the same thing will be 1. That is what we already had, and that is how we calculated the normalization constant. Okay, so we have to find the value of integral. So let us apply it. Integral 0 to a square root of 2 by a. You have a 2 by a, 2 by a's you will have. Okay, sine n pi x by a, again 2 by a sine m pi x by a dx. Now let us check. Constant can be taken outside. 2 by a, square root of 2 by a square. That means 2 by a comes out. Now, in order to make this product much more easier, because you have a product of two signs. One is sine mx and the other is sine nx. So let us simplify it. By giving a different identity, sine nx sine mx is equal to cos m minus n. Okay, either of it, m minus n x minus cos m plus n x. So this is going to be our identity, and we will apply that. So our integral is 0 to a. Yeah, 2 by a comes out. Now you have a first term cos m minus n. You have pi x by a. Then minus cos m plus n pi x by a dx. Now if you integrate, again you will find that cos becomes sine. If we can just check, sine m minus n pi x by a by m minus n pi by a is the constant, and apply limit. This is, I am doing only the first term in order to make you understand that this is also going to be 0. So this is again a sine function, and it is again, yeah, if you apply the limit, this will be cancelled. Now you will have again a sine pi of a multiplier. Again, multiplier of pi turns out to be 0. That means this integral is going to be 0. So now we have proved that the wave function is orthogonal. If you take two distinct wave functions that indicates different states, this is going to be 0.